Good morning, guys. Now we will start our second video lecture for finite element analysis. In this video lecture, we are going to derive the stiffness matrix. We will derive the stiffness matrix for one-dimensional spring element. Okay. So in previous lecture, we derived the stiffness matrix for one-dimensional bar element. So similar way, we will derive the stiffness matrix for one-dimensional spring element. Okay. So this is the spring element. Okay, of spring constant, or you can say it as a stiffness. Stiffness of the spring is equal to K. Okay, so K is called as a spring constant, or it is called as a stiffness of spring, which is nothing but force upon delta, because stiffness is nothing but amount of force required to deflect the spring with amount delta. How much amount of force is required to deflect the spring by amount delta? Okay, suppose if the spring is deflected by some amount delta. Okay, so now we will derive the stiffness matrix stiffness matrix for one-dimensional spring element in similar way as we have derived this stiffness matrix for one-dimensional element. Okay, so for this, now this is your stiffness or spring constant. Okay, now so for finite element analysis, or to derive the stiffness matrix of the spring element, there are 4 steps. Basic 4 steps are there. So first one is convert your physical or convert your real life problem into a finite element method or into a discretized problem. Okay, so discretized means convert this entire domain into finite number of elements. Okay, so here we are considering one-dimensional spring element. Okay, so this is considered to be a one-dimensional element. Okay, so for one-dimensional element, there are 2 nodes. First one is this node, first node, and second one is, suppose this is the second node. Okay, so similar to one-dimensional bar element, we are considering here also the nodal forces and nodal displacements. So for this case, suppose this is your F2 and this is your nodal displacement U2. Similarly, for node 1, F1 is the nodal force which is acting at node 1, and similarly U1 is the nodal displacement acting at node 1. Okay, so now our basic theory or simple theory says that this F is equal to K times delta. Okay, this force is equal to K times delta. So force, it can be written as F is equal to K times, now delta, deflection is nothing but U2 minus U1. In similar way, we derived during our stiffness matrix for one-dimensional bar element. Here we can write this delta as, because in your one-dimensional bar element we have considered this delta as delta L. Okay, so in similar way, we can write this delta or deflection as U2 minus U1. Okay, so if this F is equal to K times U2 minus U1 acting at node 2, then there must be the same amount of force which is acting at node 1 but in opposite direction. Okay, so there must be some force which is equal to the force acting at node 2 and which is acting in opposite to the direction of this force F2. Actually this is nothing but your F2. Okay, this is nothing but your F2, nodal force F2. So keep this spring in equilibrium position, we need to apply same amount of force K times U2 minus U1 in opposite direction acting at node 1. Okay, so this F1 will become minus of F2. Okay, so in this way we can identify the force acting at node 1. Okay, actually this is for your basic, this is for derivation purpose actually. So if the force F2 is equal to K times U2 minus U1 is acting at node 1 in tensile direction, then there must be same amount of force which must act at node 1 in opposite to the direction of force F2. So your F1 will become minus F2. So it will become F1 is equal to minus times K in bracket U2 minus U1. Okay. So actually in previous derivation, instead of K we have written as A by L. Instead of K we have written A by L, or we have derived this A by L by using this deflection formula. Means during the bar element we have derived that we know that delta is equal to PL upon A. So P by delta, it will become A by, and A by L is nothing but, because P by delta is nothing but your stiffness, or the stiffness of that spring. So instead of K we have written A by L during our derivation of one-dimensional bar element. For one-dimensional bar element we have considered this stiffness is equal to A by L. But here the stiffness spring constant or stiffness of the spring is given. It is equal to K. So we can write, instead of A by L, we can write this as a stiffness coefficient or stiffness of the spring or spring constant K. Okay, so in this way we will get two equations. F2 is equal to K times U2 minus U1 and F1 is equal to minus K times U2 minus U1. Okay, so basic thing is that if the force F is equal to K times delta is acting in tensile direction, okay, then there must be same amount of force which must act at node 1 in opposite direction. So this will become F1 is equal to minus of K times U2 minus U1 and F2 is equal to K times U2 minus U1. Okay, so in this way we will identify the forces acting at node 1 and node 2. Now these equations, these two equations, now we are going to simplify and we will write these equations in a matrix form. Okay, so how to write these equations in matrix form? So now first F1 is equal to minus K times U2 minus U1. Okay, U1 and U2, these are the nodal displacement acting at node 1 and 2 respectively. Okay, and now this F1, it can be simplified as F1 is equal to minus K times U2, this minus minus gets plus K times U1. Okay, so we can write this equation as F1 is equal to K times U1 minus K times U2. Okay, and this F2, now simplify the F2 in similar way. So F2 will become F2 is equal to K times U2 minus K times U1. So you can write this equation as minus K times U1 plus K times U2. Okay. In similar way that we have derived during our stiffness matrix for one-dimensional bar element, here instead of this K, we have written A by L and we have derived our equation or our matrix. Okay, so similar way we will derive the same stiffness matrix for the one-dimensional spring element. Okay, so suppose this is equation 1 and this is equation 2. Now equation 1 and equation 2 can be written as, so F1 is equal to K times U1 minus K times U2 and F2 as F2 is equal to minus K times U1 plus K times u. Okay, so suppose this is equation 1 and equation 2. Now we can write these two equations in matrix form, as we have already written the algebraic equations into matrix form during your numerical methods and optimization subject also, and during our last derivation also. Okay, so write these two equations in matrix form. So first there will be a force vector F1 F is equal to, okay, these two forces are considered to be a force vector in your matrix form. So this is your force vector F1 F2 is equal to, now is equal to first term, actually this is your u1 and u1 and u2 is nothing but your displacement vector. Okay, so from this u1 and u2 you can write this matrix as k minus k, k minus k, and for this case minus k. Okay, so this is nothing but your force and displacement relationship for a one-dimensional spring element, and this is nothing but your stiffness matrix. This is nothing but your displacement vector, and this is nothing but your force vector. Okay, so in this way we have derived our stiffness matrix for one-dimensional spring element. Okay, so this is the stiffness matrix for one-dimensional spring element. So in this way you can write the stiffness matrix for one-dimensional spring element. Okay, now see here spring element. Actually this is we are considered only one element between node 1 and. Okay, so this stiffness matrix, actually this can be actually we have written this stiffness matrix between nodes 1 and 2 as between node 1 and 2, between node 1 and 2. Actually, as these two equations is nothing but F1 is equal to k times u1 minus k times u. So this element or this parameter is nothing but your A11 position of the matrix. This parameter is nothing but your A12 position of this stiffness matrix. Similarly, F2 is equal to minus k times u1 plus k times u. Now this k is nothing but your position. We can write the position of this element as A second row first column, second row first column. Then this element can be written as second row second column, second row second column. So this is nothing but if there are only two elements 1 and 2, then matrix will become of order 2 by, matrix is of order 2 by 2. Okay, so and the elemental positions are like between 1 and 2, between 1 and 2, like A11, A12. From first equation you will get A11, A12. From second equation you will get A21, A2. Okay, so for one element only, the matrix will become, elemental stiffness matrix will become A11, A12, A21, A22. So in this way, we can write elemental stiffness matrix for spring element. Suppose, now, okay, this is your derivation for the stiffness matrix. Now, if there are two elements, now, if we consider if there are two spring elements, okay, actually this is the matrix. Instead of A11 you can write K minus K, K, and the position of this stiffness matrix, order of this stiffness matrix will become 2 by 2 by 2 because there are 2 nodes. So number of nodes equal to the order of your stiffness matrix. Okay. So if there are 2 nodes, there must be 2 by 2 matrix. If there are 3 nodes, there must be 3 by 3 matrix. If there are 4 nodes, there must be 4 by 4 matrix. Means you will get the stiffness matrix of that node order. Means if the number of nodes are equal to n, if the number of nodes equal to n, then your order of that stiffness matrix will become n by n. Okay. So if the number of nodes equal to n, then order of that matrix will become n by n. Okay. Now if there are 2 spring elements, suppose there are 2 spring elements with spring constant K1 for the first spring element and spring constant K2 for second spring element. Then how to write the stiffness matrix for this 2 elemental case? Now, as we know that if there are 1 element, then there must be 2 by 2. 1 element means there are 2 nodes. Then the order of that matrix will become 2 by 2. Here, there are 2 elements. Okay. So, if there are 2 elements, then nodes, how many nodes are there? So, this is your first node, this is your second node, and this is your third. Okay. So, there are now 3 nodes. So, if there are 3 nodes, means number of nodes n is equal to 3, then your global, now the term global stiffness matrix. This is your elemental stiffness matrix. Okay. This is your elemental stiffness matrix for only 1 element. But for this case, we need to construct a global stiffness matrix by using elemental stiffness matrices. Means if there are 2 elements, then there must be 2 elemental stiffness matrices should be there. Okay. So we need to construct a global stiffness matrix K. Okay, and order of that global stiffness matrix K will become equal to 3. Okay, or 3 by 3. Okay, so we need to construct the global stiffness matrix. Now, how to construct this global stiffness matrix? By using these elemental stiffness matrices. Means for element 1, there must be some elemental stiffness matrix. For element 2, there must be some elemental stiffness matrix. Okay, so by using this elemental stiffness matrix, we are going to construct our global stiffness matrix K. Okay, so this K will become of the order 3 by 3, and we can write it as K11, K12, K13 for first equation, K21, K22, K23 for second equation, and K31, K32, K33 for third equation. Okay. So we can write or we can construct this global stiffness matrix. Actually, this is nothing but your global stiffness matrix. Okay, so this K is nothing but your global stiffness matrix, and the order of that global stiffness matrix will become how many nodes are there? There are 3 nodes. So it will become the order of that global stiffness matrix will become 3 by 3. Now, how to construct this global stiffness matrix? Okay, actually, position of this global stiffness matrix is 1, 2, 3, then 1, 2, 3. Okay, so how to construct this global stiffness matrix by using this elemental stiffness matrix. Now we will see this. Okay, so now we will construct our global stiffness matrix. Okay, as we know that I will write this global stiffness matrix here in the corner. So finally, we are going to use this global stiffness matrix for constructing. So this is your K11, K12, K13, K21, K22, K23, K31, K32, K33, and its position is 1, 2, 3, 1, 2. Okay, this is the reference I have written at the corner. Now we will construct our global stiffness matrix. Okay, for element 1, we can write our elemental stiffness matrix as elemental stiffness matrix. Suppose this is A1 as the elemental stiffness, sorry, instead of A1 we can write E1. This is your elemental stiffness matrix E1 for element 1. Okay, now this element 1 actually it lies in between node 1 and 2. So it will become between 1 and 2. Okay, between 1 and 2. So we can write this elemental stiffness matrix by using our stiffness matrix for one dimensional spring element, as this will become K1 minus K1. For first equation it will become K1 minus K1. Second equation it will become minus K1 K1. Okay, so in this way you can write the elemental stiffness matrix E1 for this for this first element. Okay, K1 minus K1 minus K1 minus K1 plus K1. Okay, because we have derived this, we have written this stiffness matrix for one dimensional spring element as K minus K K into U1 and U2. Okay, so this is the stiffness matrix for one dimensional spring element. Similarly, we can write by using this equation our first elemental stiffness matrix as, because instead of K here the spring constant is K1. So for elemental stiffness matrix E1 it will become K1 minus K1 minus K1 K1. From this equation, this is actually your equation for one dimensional spring element. This is the generalized equation for your one dimensional spring element. Actually we have derived. Okay, so by using this equation or by using the value of this stiffness matrix from this equation, you can write the elemental stiffness matrix E1 will become K1 minus K1 minus K1 K1. But the position of this elemental stiffness matrix, actually this spring element lies between node 1 and node 2. So you can write this between node 1 and node 2, between node 1 and node 2. Similarly, now elemental stiffness matrix K2 will become, sorry, E2. Elemental stiffness matrix E2 will become, now this element, spring element lies between node 2 and node 3. So the position will become between node 2 and node 3, between node 2 and node 3. Okay, so this will become, instead of K here value is K2. So instead of K we can write K. So it will become K2 minus K2 instead of K, minus K2 instead of K, K. Okay. So in this way you can write the elemental stiffness matrix for second element also. Okay. So now construction of the global stiffness matrix. Okay. So now see, your global stiffness matrix will become of order 3 by 3 because there are 3 nodes 1, 2 and 3. As there are 3 nodes, so your global stiffness matrix will be of order 3 by 3. But your elemental stiffness matrix here, this will lie between node 1 and 2. But for construction of global stiffness matrix, we need a 3 by 3 matrix. Okay. So you can write this as 3 and also, but the remaining elements will be 0. Okay. You can write this because this is your null values are there. Because if you write this equation as by using this first law, you will get k1 times u1 minus k1 times u2 and 0 times u2. So it will not affect your stiffness, elemental stiffness matrix. And why we are doing this? Because we have to construct our global stiffness matrix. But global stiffness matrix is of order 3 by 3 because there are 3 nodes 1, 2 and 3. So we need to write this elemental stiffness matrix in that format. Means it should be a 3 by 3 matrix. So we can write this as the third column it will be of 0 elements and third column it will be of 0 or null values. Okay. Similar way, E2 we can write. Actually, E2 is between 2 and 3, but we need first row and first column. So let us say, suppose this can be written as, without affecting the initial matrix, we can write it as, actually it is between 2 and 3. So we can add our first row as well as our first. This is your first column of null values. Similarly, first row. Okay, so you can write actual elemental stiffness matrix is in between node 2 and 3. But for constructing of your global stiffness matrix, or for the purpose of this global stiffness matrix, we are writing this elemental stiffness matrix in a 3 by 3 form. So it will become 0, 0. Your first row will become 0 or null value, and first column also have a null value. So in this way, you can write your elemental stiffness matrix E2, where first row has null effect, first column has also null effect. Okay, so now by using this E1 and E2, you can write your global stiffness matrix. Means simply addition or simply positioning of these elements into the global stiffness matrix, you will get the global stiffness matrix. So you can write it as, now your global stiffness matrix will become, okay, it is of order between 1, 2, 3, between 1, 2 and, so write down elemental stiffness matrix between position 1, 2, 3. Means map this E1 into global stiffness matrix as K1 minus K1 0, then minus K1 K1 0, then 0 0 0. Similarly, map this your E2 in this form. So first one is 0 0 0. So 0 plus K1 it will become K1. 0 minus K1 it will become minus K1. 0 plus 0 it will become 0. Now second, 0 K2 minus K2. 0 minus K1 it will become minus K1. Now K1 plus K2. Here it will become K1 plus K2. Or simply you can add these two matrices to get your global stiffness matrix. So by addition, this will simply by addition K1 becomes K1 plus 0, K1 minus K1 plus 0, minus K1, 0 plus 0, 0. Similarly, minus K1 plus 0, minus K1, K1 plus K2, K1 plus K2. Then 0 plus minus K2, so it will become minus K2. Then for third row, 0 plus 0, 0. 0 plus minus K2, it will become minus K2. And 0 plus K2, it will become K2. So, in this way, you can construct the global stiffness matrix between 1, 2, 3 position. So, you will get the global stiffness matrix for the two elements. Now, I will give one example for construction of, if there are three elements, three spring elements, then construct the global stiffness matrix. Suppose this is your homework. Suppose K1 is equal to 100 kilonewton per meter. K2 is equal to suppose 70 kilonewton and K3 is equal to suppose 100. Instead of 100, 700 kilonewton. And the question is construct the global stiffness matrix. First question is find out elemental stiffness matrices. And second one is construct global stiffness matrix. Okay, so this is your homework, and I will construct the global stiffness matrix in your next lecture. But try to construct your global stiffness matrix by using this. K1 is equal to 100 kilonewton per meter, K2 is equal to 70, and K3 is equal to 700 kilonewton. And this order of this global stiffness matrix should be of, as there are how many number of nodes are there? This is 1, 2, 3 and 4. So your global stiffness matrix will become of order 4 by 4. So try to construct this global stiffness matrix. I will construct this global stiffness matrix in your next lecture. Okay, so we will conclude our lecture here. Thank you.